Word. All right. Wow. I can't remember if I've written it before, but it does not hurt. Final exam is on April 17th from 9 to 12, I think. I had it open. E208. Nice. Nice. So that'll be good. And then you can purge all the stats from your mind forever. Forever. I guess I shouldn't say that in the recording.
You don't expect to be able to have long stats screens?
Well, what's pretty fun is I have had quite a few people message me. This was when I was teaching up at UBCO mostly. And they would go to like Sauder School of Business or whatever. And afterwards, and they're like, Emily, thank you so much. It turns out I actually do know stats better than like other people in my class. So I was like, well, that's pretty good. So you'll use it, just maybe not all the time. I left you with a question to work on. Oh, right, Emily, I totally forgot. I know. Okay, let's see here. Just gonna grab this here, copy. Continuing from last day. Guess I should refresh our memories of what the question was about. I think it was about piano lessons. Really important stuff here. You can do hypothesis testing for anything. Clearly. Okay. I'll just go back, reread the question. All right. So Georgiana claims that in a small city renowned for its music school, the average child takes less than 5 years of piano lessons. We have a random sample of 20 children from the city, from this small city, not the city, sounds weird, with a mean of 4.6 years of piano lessons and the standard deviation of 2.2 years. So last day we started talking about inference for one sample means. Right, and so now I have one sample of 20 children and I have the sample mean and the sample standard deviation. And so that's my clue that, okay, now this is a means question, not a proportion anymore. Okay? And we talked about the conditions. The conditions are relatively simple for what we call t-tests. We have to check independence. If the sample was randomly selected, then you can assume independence. And then there's the normality condition, where if the sample size is less than 30, you have to make sure as best as you can, given the information that you have, that there are no extreme outliers, okay? And you have to assume that the distribution is approximately normal. If it's greater than 30, so if you have a large enough sample size, then you can just go ahead and assume normality, right? You're barring any huge outliers, you're safe. Okay, so that's really nice, kind of relaxed conditions for the t-test. Just as before, for proportions, right, our hypotheses have to be about the parameter. Now for the mean, right, the population mean is mu, right? So we're talking about how mu compares to some number. And we said, okay, well, Georgiana actually suspects that she claims the average child takes less than 5 years of piano lessons. So then our alternative hypothesis is going to be that mu is less than 5. Right? 4.6 is less than 5. We would just want to know if it's significantly less than 5. Okay. So from the formula sheet, we know that we calculate a t, which looks very similar to a z, right? It's just that we have s over root n. And we found a t of negative 0.813. Just as before with the z, we take the absolute value because it's symmetric, so we don't need to have both sides. And we also need the degrees of freedom now when we have a t. Okay? But the degrees of freedom is just n minus 1, so we have 19 degrees of freedom. Just as a reminder, right, if you find yourself needing some degrees of freedom that isn't explicitly in the table, right? So 57 degrees of freedom, for example, right, goes 50 to 60. You'd be tempted to go for 60, but you shan't, cannot, should not, will not. You'll go to 50, make up words as I go, right? Because otherwise you're assuming you have a larger sample than you actually do, which is bad, right? But notice the difference between these values is minimal, right? So it's not a big deal. It's just doing it properly. Okay. Then, so now we can pick up in our notes today. So we found 19 degrees of freedom. 19 degrees of freedom is on our table. So now you can just ignore all the rest, right? You can ignore all the other degrees of freedom because your sample size is not going to change, right? And then we can find the p-value the same way that we did for z's, right? But now we have to trace down a little bit further, depending on if you have a one-sided test or a two-sided test, right? That'll determine if you need the one-sided p-value or the two-sided p-value. So
how do we know that if we want one-sided or two-sided?
Because it traces all the way back to here. Okay. So if you only care about one extreme, so less than or greater than, then you have a one-sided test. Okay. Whereas if you just want to know if mu is not equal to 5, right, then you don't care which tail as long as it goes into one of the tails. So then you have a two-sided test. Now, what we're doing is running them side by side because kind of inside scoop, the textbook made one-sided tests optional. I'm not making them optional, but they did, so that's why it's worded weird. So evaluate Georgiana's claim, which was that they take less than 5 years of piano lessons. And then they had to add, or that the opposite might be true, which would result in this two-sided test, right? But we're gonna run both of them side by side up until the p-value, which is where we got to. So here, our one-sided p-value is somewhere between 0.2 and 0.25, right? We'd need software to pinpoint that value. It exists, but this is good enough for us. And then the two-sided p-value is even bigger. So that's why they made the one-sided tests optional, is because it's a little bit risky, easier to reject H0, right? Because your p-value is just going to be smaller. And so to guard against that, really what we should be doing is just always doing a two-sided test. So that's your default, right? Unless it's obvious in the question, right? Is it less than 5? Which it is here. So we're going to use this for our conclusion. So step 4 is our conclusion. I use the same layout as I was before, right? So we have to compare the p-value to the alpha level. We weren't given an alpha level, so we're just going to assume 0.05. And then what does that mean in terms of H0? And then what does that mean in terms of the question? So here we go. Since the one-sided p-value is between 0.20 and 0.25, it is not less than the assumed alpha level. Oops. of 0.05, which means we do not have enough evidence to reject H naught. Which means we do not have enough evidence to reject H naught. This is your chance to show off everything that you know, right? And nothing is hard here. You're just really explaining your thought process, right? So since the one-sided p-value is between 0.2 and 0.25, right? So usually what I see is you feel like you need to kind of cut down on time, and then you say the p-value is greater than 0.05. But if you just tell me what it is, it also gives you a chance to check in and say, well, is what I'm saying true? I see that a lot of the time, right? You're in such a rush, and then you say something that's, it is less than the assumed alpha level of 0.05. As long as you follow through with the correct conclusion, I'm okay with that, I guess. Especially in the beginning, I'm okay with that, right? But by the final, it should be kind of on rails. All right. Therefore, whoops. What does that mean for Georgiana's claim? Therefore, I'll say, therefore, there is no evidence to support. How does she spell Georgiana? Has to be a long name, I guess. Georgiana's claim. And let's just, why not throw in what the claim was, that the average child takes less than 5 years of piano lessons. Takes less than 5 years of piano lessons. All right. So we did part A. Part B, of course, we're going to make a confidence interval. Wait, hey. Construct a 95% confidence interval for the number of years students in the city take piano lessons and interpret it in context of the data. So we know from the formula sheet, where is it? Just gonna mark this up so it bumps it up. Bump it up. We know from the formula sheet that the confidence interval looks like this, but also we know enough about confidence intervals and how they are built in general, right? It's going to be the point estimate plus minus the margin of error, where the margin of error is some critical value that determines the confidence level, right? Or translates the confidence level times the standard error of the point estimate, which in this case happens to be S over root n. Right. So we had all those components and we built this up last day. And so now we're just going to use it. Okay. So our X bar was 4.6. Let's see here. So X bar is 4.6. S was 2.2 and N was 20. Now you're welcome to, on the quiz and the final exam, if you've already calculated S over root n, which we did, right, when we calculated t, then you can just recycle that number. You don't have to recalculate it. You can just use it again. The only thing that's missing here is T star at n-1 degrees of freedom. So we have T star at 20 minus 1. You don't have to be that explicit, but technically it's true at 19 degrees of freedom. So then, let's see here. I'll grab this because this is what we need now. And I'm going to grab the 19, the block that has 19 degrees of freedom. Nice. I'll leave a little bit of room here. So again, we have wait, hey, what happened? Come on. We have 19 degrees of freedom. And we want to build a 95% confidence interval. So it's the exact same as what we were using or how we were using this table before. It's just now we're able to move around with the degrees of freedom. All right. So our T star, our critical value, 2.093. Saying critical value, we've used that in a different context as well, right? When we said, okay, if our chi-squared is bigger than this value, then I have enough evidence to reject H0. So if I go back up here, we could use the critical value approach, right? We have a one-sided test. If I force the tail area to be 0.05, at 19 degrees of freedom, my T has to be bigger than 1.729 in order for me to reject H0. So you're allowed to go that route, but I also don't want to confuse you too much, right? So if that route makes more sense to you, then you're welcome to use it. But I'm just going to use the p-value approach always because it's kind of more widely accepted. Okay. So you can use it, but then it's a critical value in the sense of, okay, my T has to be bigger than this value in order to reject H0. Here, the critical value has to do with, well, this determines what my confidence level is, right? The only thing that tells my confidence interval what level of confidence it is that T star, right? So we call that a critical value. Okie dokie, artichoke. Here we go. X bar plus minus T star times S over root n. So we have 4.6 plus minus 2.093 times 2.2 divided by the root of 20. Just as a heads up, people love to kind of be thrown off by this. This is just your n. Right. And then so sometimes people are like, no, it's n-1. No, it's not. It's just n, right? So just let the formula be your guide, right? So it's just n, don't do n-1 here. Degrees of freedom is n-1, but not here. All right. So, and these are from last day. Oh, guess not. 4.6 plus minus 2.093 times, and I have 0.491934955, which if you guys are okay to accept blindly, then great. 4.6, because I am. 1.02961986 To refresh our terminology, right, this here is the margin of error. Unlike when we were dealing with proportions and we were able to solve for n, we won't be able to do that because the margin of error involves a measurement from the sample that we wouldn't have, right? So we would need some guess at what that population proportion or population standard deviation is, and that's kind of unrealistic. So, so we won't be able to solve for n. So that's one thing that you can't do when you're in a means type question, unless you pretend to know the population standard deviation. Right? Then you can, but we're not going to do that. So we get an interval from 3.5703800139 up to 5.6296198661. Or if I'm going to round, I'll just go to 2 decimal places, even though the answer or the values given was only to 1 decimal place. So you would be safe to go to 1 decimal place, right? You just want to match whatever, match or outdo whatever was given in the question, right? So here they give 1, I'm going to give 2, just makes me look better. 3.57 to 5.63. Our interpretation stays the same, right? Except now we're talking about the population mean, right? The population mean amount of years spent in piano lessons, right? For an average child, right? So we are 95% confident the interval from 3.57 to 5.63 years captures the true number of years children in this city take piano lessons. Children in this city take piano lessons. I'm just going to see if that matches how the question was worded. Oh, I thought students was kind of weird, so I changed it to children, I guess. But construct a 95% confidence interval for the number of years students in the city take piano lessons. So now we are 95% confident that the interval from here to here years captures the true number of years. And I guess I'll match the question, students in the city. Although I could have sworn it was children in general, but that's on them. They mucked it up, not us. In the city take piano lessons. And so just reword the question as an answer, and then you've got it. Confidence intervals are equivalent to 2-sided tests, right? Because confidence intervals go in the center, and then you have tail area on both sides, right? So they're not going to match a 1-sided test necessarily. Usually they do, but not necessarily. Sometimes there's a little bit of wiggle room, okay? But you can use this interval, right? 5 is in this interval, so 5 years. We're 95% confident that 5 years of piano lessons is a perfectly reasonable population mean, right? And so that would be, so again, this is just evidence against her claim. What would be evidence for her claim? Then your whole interval would have to be less than 5, right? So this would have to be 4.63 or something, right? So I'll make a note of that here. And maybe I'll do it on a fresh page. Note, confidence intervals match, I'll put it in quotes because it's not proper, but I think it makes sense. Confidence intervals match two-sided hypothesis tests. Right, and it's because it looks like this, right? So you're either 95% confident that it's between these two values, or there's a 5% chance that you're wrong, right? So that's how they're related, right? And so we can use this interval to informally confirm the claim, right? Even though it's a one-sided test. So we can use the confidence interval to informally test Georgiana's claim. And since 5 years of piano lessons is in the interval, right, is in the 95% confidence interval. This is evidence against her claim. Against her claim that children take less than 5 years of piano lessons. Fine. That children take less than 5 years of piano lessons. Oops, it's not a quote. Hey, I guess this was part C. I just wanted to say it, but let me just insert it so we can check it off our list. Do your results from the hypothesis test and the confidence interval agree? Explain your reasoning. Well, we just did, except gonna have to put the question on the previous page. Have to. No, I don't. I can give myself more room. Okay. So how we use confidence intervals and hypothesis tests are just slightly different. Okay? So what does a hypothesis test do? It told us that, okay, it's not significantly different from 5, okay? Because we didn't have enough evidence to reject H naught, right? Which said that mu is 5 or basically 5, right? Not significantly different from 5. But then the confidence interval actually gives us a range of plausible values, right? I don't know what it is exactly, right? But here's my guess at where the population mean is, right? So it gives us a range of values that it could be, right? It's kind of a lot more useful if you had rejected H naught, right? So mu is less than 5, great. That doesn't tell me anything. What is it then? Then you follow up with a confidence interval. So you usually do both. right? So you do a hypothesis test, and then if it's significant, then you do a confidence interval to figure out, okay, well, what is it then, right? And so hypothesis testing let's see. I think I had it written down in a nice way. Maybe not. Determines if there is a significant difference whereas a confidence interval tells us what the difference or what the value might be. Tells us what the value might be. I kind of wanted one. Okay, the next example gives us a better idea of this, but this is good to establish now. All right, so one sample mean questions are different, right? But they're not too bad once you kind of get into it, right? We have all the tools that we established in the proportion questions, and then we just kind of apply it to a slightly different scenario. Just remember that you're talking about the mean instead of a proportion, right? So numerical data instead of categorical data. Now, (7.2). Next section, next question type is on paired data or matched pairs. Sometimes I call them matched pairs, really just to emphasize that they're kind of matched. Yeah. So here, what do I call it? Oh, I even called it that on the formula sheet, paired data or matched pairs. Now we're going to be talking about the mean difference. Okay, so before we kind of look further into the formula sheet, I want to kind of establish the premise first. Okay? So we're going to have two samples. Okay, so now we're moving into two sample means questions. Okay. But the first type is the special case where an observation in sample 1 can be paired to an observation in sample 2, right? So for example, if I look at your quiz 1 scores and then I look at your quiz 2 scores, right? Then I want to capture that, okay, well, I mean, my test 1 score or my quiz 1 score, right? I'm at some level of knowledge, right? And I'm presumably going to carry that with me, right? Into quiz 2 and so on and so forth, right? And then, and we kind of use quiz 1 as a guide, right? Oh, I did a lot better on quiz 2, or I'm improving, or, oh, that was a terrible quiz for me, whatever, right? But how we do that is we look at the difference between those two scores. Okay? And so usually I talk about kind of me in a running clinic or something like that. I'm not a runner by any means. And so obviously I'm not very fast, I don't think. And so I go in and I enter this running clinic and they're like, great, can you run around the track? Sure thing. So then I have my starting time, right? The time that I took to run around the track when I first started the clinic, right? And then I go through and I learn all these things and I get stronger, hopefully, right? And then they ask me to do the same thing again. Okay, now go run around the track. It's a month later. I don't know how long it takes, but hopefully I've improved, right? So then I do the same thing again, right? And even though I, as a person, am a slow runner, right? My next time should be faster than my first time, right? If I have improved. So we capture that, whereas maybe Robin, you're a crazy fast runner, right? And you start fast, but then you still got faster, right? And so then that would be reflected in the differences between the two times. So what's kind of fun and honestly pretty cute with paired data is that even though we have two columns, right? You have your first run and then your final run, right? So we have two samples, but what we do is we calculate the differences and then we just analyze the differences as if that's one sample of differences. Okay. So for example, right, my first run, I don't know how long it would take me. How big such, I don't know, 5 minutes. Right, so here, Emily 1, Emily 2, just because I shouldn't write names in here. And I'm not creative. Well, actually I am here. Emily, and then Steve hits the track. And then Joya hits the track. I can use their names. All right. Steve did it in 2 minutes because he's just crazy fast, right? Joya did it faster than me, but I'll hold her back a little bit, 4 minutes, right? So then the final run, I did it in, how flattering should I, 3 minutes seems reasonable, right? Who knows how long it takes. Steve did it in 1.5 minutes. There wasn't that much room for improvement, right? But he improved. And then how mean should we be? How about 4 minutes? Joya's just a steady state runner, right? Okay, so now, right here, we have sample 1, and here we have sample 2, right? So we have 2 samples, but then what we do, the trick is we find the difference, right? And I'm gonna go first minus final. How you find the difference has to be consistent for all the columns, right? But the order that you find the difference, it doesn't matter. You could have done final minus first. Sometimes because I hate negatives, I just kind of look at how I avoid negatives. But maybe that's overkill. Here, I'm avoiding negatives. Why? My first run's slower than my final run. Times are kind of tricky, right? Low times are better than long times, but so here the difference, now we have 1 sample of differences. So here the difference is 2 minutes, 0.5 minutes, and 0 minutes. So now, right? Now you have, we can find X bar of the differences, right? The mean of the differences. We can find the standard deviation of the differences. And I also have some number of differences. And that's the one that throws me for a loop, or at least when I was first starting this, and I would always say, well, actually I have 6, don't I? No, right? Because once you've calculated the differences, these guys are as good as gone. How do I? Right. You've captured all that activity of the two samples in your one sample of differences. So now you just put those out of your mind, and now you're just here, right? So now you have a mean of the differences, and I like to emphasize that it's the differences just because that points me in the direction of a matched pairs or a paired data type of question, right? And so here, what I'll say is, once we have calculated the differences, we can, and I'll say discard them. You're not going to discard them, but kind of from your mind, right? We can discard the original two samples. You do have two samples, right? So it is a two sample means question, but it's a special type where they're paired. Okay? So some common examples, and maybe I should talk about this. Once we have one sample of differences, we apply the one sample means strategies, right? Which is what we just covered. Okay. So that's when I'm going to bring in this formula sheet here. And we'll stare at it long and hard. No, not really. We'll look at it and say, oh yeah, that checks out. That all looks familiar. So now I have a little note here saying that you're analyzing the mean difference, right? So the mean of the differences. Okay. Just as kind of a roadmap. If you go to, because of course we could end up having two sample means, so two independent samples, there's no way to match them. That's the next thing that we're tackling, right? What if I can't match them, right? You don't have to, right? Group A, group B, completely independent of each other. How do we compare the two? Then we're talking about the difference of two means, right? So it's the mean difference versus the difference of means. Very subtle change in terminology, right? But it's going to make a huge difference. Did she just say difference again? Oh man. Don't worry, it gets worse. The alternative, the null hypothesis is going to be about the mean of the differences, right? And it's always going to be, how does the mean of the differences compare to zero, right? If the mean of the difference is zero, there's no significant difference between group one and or the pre and the post scores, for example, right? And then the alternative then is the mean difference significantly different from zero. So many differences. You just got to keep them all in line. Besides that, though, besides all these differences, nothing has changed. In fact, I've seen some formula sheets where they don't even specify this, right? You just go back to one sample mean and use those techniques, but I like to have it explicitly, right? But all I've done is just put little diffs everywhere to emphasize that it's the differences, right? But you are back to one sample mean strategies. Okay. The only, how do I say difference without saying difference? The only difference is that now you know what mu naught is. Mu naught has to be 0, right? Otherwise, there is a difference between the two groups, right? So what are some common paired data situations? Common paired data situations. Pre-post scores are kind of the most common. So you've got pre-post scores, right? If you're talking about maybe twins, for sure, there's a really common example of they were testing runners with little boys. That sounds weird. But so they had one type of runner on the left foot and one type of runner on the foot, and they were randomly assigned, right? And then they just kind of said, oh, okay, wear these in your daily lives for, I don't know, for 2 weeks. And then they measured how well the rubber on each shoe held up, right? And so that would be a paired test, right? And so kind of same subject, 2 measurements. Even when we want to do things like how do they decide where to put like those wind turbines, for example? You don't just go put one out willy-nilly, right? You go and you put up little measurement towers, right? And then right, you've got different sites that you're looking at, and then on the same day, right? If it's a windy day, then both sites are going to have lots of wind, but one's going to be better, right? On a non-windy day, neither of the sites are going to have that much wind, but one is going to be better, right? And so then it's paired on the day. So there are lots of different ways that you can do it. Even kind of a stretch like married couples, for example, depending on what you're measuring, right? And so sometimes kind of married couples, and what I mean by that is, okay, so you're married for a reason, right? You've got your similarities or whatever. And it doesn't have to be the same subject, right? They can be similar subjects, right? So here are similar subjects. But paired data, just in general, is, or paired data is when we've made 2 measurements on the same subject. And I'll put same in quotes because it's not necessarily exactly the same. 2 measurements are made on the same same subject, right? Not necessarily exactly the same, but usually. Now, how did I say it here? Just in case I had something clever. Nah. Okay. Let's do an example, which I'm just realizing now I might have to hunt down unless, hey, what's going on here? Unless I can figure out. November 15th. When I did it. I had these printouts once upon a time. Let me just see if I can find them. No, but close. Can I search in here? I can. Chapter 5. Oops. It's about Jocko's garage, which just sounds bad, right? He's gotta be. Duh. Finally, okay. There's lots, I have some examples that I'll give you guys, but here. Finally. Now let me just bring this in here. And then I won't be able to find it next term. Is it still doing that thing? It's probably weird. Probably for the best. It's kind of fumbling a lot. All right. So insurance adjusters are concerned about the high estimates they're receiving from Jocko's garage. Yeah, right. To see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's and to a trusted garage, and the estimates were recorded. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? Okay. So we've got 10 cars. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. I can count to 10. We've got the estimates for Jocko's garage, right? 500, the trusted garage says, oh, I'll do it for 430. Jocko says 1550. The trusted garage says 1500. Oh, but what's this? Jocko says, oh yeah, I'll do it for 1250. The trusted garage says, oh, it's going to cost us 1300, right? And so the damage of the car determines what the quote's going to be, right? You can't just do a low quote. If there's a ton of work to do, then you're going to have a high quote, but you're going to have a high quote in both of the garages or at both of the garages, right? And so because we have each car getting 2 measurements, right? Then that's why this is going to be paired data. So paired data, since each car has 2 measurements or quotes, if you prefer. So that's your first step, right? Figuring out what type of question it is. And the more of these you see, I find that the paired data kind of jumps out at you more obviously than the other ones. And so you can kind of pick it out of a crowd pretty quickly. Okay. So let's see if I have the differences, but I just don't have them on here. So what would we have to do? First things first, these are decoys. I have the mean and the standard deviation of the individual samples. I could do that, right? But what am I assuming then? I'm assuming that it's all different cars, right? I have 10 cars from Jocko's garage, completely separate from the 10 cars that I sent to the trusted garage. That's not going to help me much, right? I need that link on the car in order to kind of have a reasonable analysis. So these are decoy numbers. Just get used to that, but I have them there for a reason. Don't worry. There's a method to my madness. So then what we do is we're going to need to find the difference. I usually just calculate the first column minus the second column, right? Just makes it easier for me to look at. So I'm gonna make a note how I calculated the difference. J minus T, and then I have, I'll just jot them down here, 70, 50, negative 50, 20. You don't need these values. I'll give you the values that you need. Negative 30, 130, 90, 160, 150, and 210. Right. Negative values mean that Jocko's estimate was actually less than the trusted garage. There aren't a lot of them, right? But they're in there. So then, now that I've calculated the differences, remember, you can just kind of ignore the rest of the information. If we calculate the mean here, we get 80. The standard deviation, if we use some sort of calculator, we get 84.59052. What throws people off is that, okay, if I have these means, then you're probably gonna want to say, okay, I can do this minus this mean, and because of how means work, right, they're just sums divided by some value, right, it does equal 80. Okay. However, that's not true for the standard deviation. So standard deviation has a square root in there making a mess, and so it doesn't translate that well, or that way rather. So this minus this does not equal that standard deviation. So just for practice, I can't remember if I have one on the assignment or anything like that. I might get you to calculate the standard deviation, because that's just emphasizing that it's not just going to be the difference between the standard deviations, right? So here I'm going to say, notice that if you subtract the two, you don't get that same standard deviation. But from here now, I have n diff is 10, right? The number of differences that I have is 10. And that's why I like that subscript diff on there as well, right? Because, okay, the number of differences, like I said, I struggled with that a lot, right? Well, I had 20 measurements, but 10 differences, right? This is X bar of the differences. Why is it X bar? Because it's a sample mean, right? I just have a sample of 10 cars. They definitely work on more than these 10 cars, right? Question.
Yeah, how did you get a S again? Like, is that, we calculate that from descriptive statistics formula?
Yeah, I would just use software, just kind of plug those in, and because 10's a lot.
So
Right.
are we gonna be given S?
Yeah.
Oh, okay.
Yeah, I think I have this vague memory on the assignment where I make you find S, but not on a quiz or the final exam or anything. It'll be given to you, right? So don't worry, but it's just to kind of remind you that you have to calculate it, and you can calculate it. It's just really boring. And then, so yeah, this is the standard deviation and the sample standard deviation of the differences. Okay, so quite a large spread, 84.59, right? That's huge, right? So even though 80 is a lot, right? Is it significantly different from 0 once we take into account this spread? That's what we're here to find out. Okay. When we say is evidence, that's like a key phrase that we use, and you have to do a full hypothesis test, right? So is there evidence that this is what's going on, right? So this tells you that we're doing a hypothesis test. I think I had some subparts, but I think we can just kind of wing it from here. It's probably down here. Mark it up. Okay, we already did all this. Yeah, let's do it. We got this. So we want to do a hypothesis test, and our hypothesis is Jocko's estimates are significantly higher than the estimates from the trusted garage. First thing we want to do, though, is check the conditions. Your first condition, and what's nice is the conditions are the same if you're doing a hypothesis test or a confidence interval. And so if we check the conditions, we're free to do whatever we want, but we do have to check them first. So the first condition is independence. They didn't tell us that these were randomly selected damaged cars. So what do we have to do? We have to assume that all the cars are independent of each other, right? That's fine. So we assume the cars, the cars are independent of each other. We can't say that the quotes are independent of each other because we just said it depends on the car, right? If there's a lot of damage, right, or not a lot of damage, then the quote will be reflected in that. But so the independence is on the cars. So we assume the cars are independent of each other. The second condition is the normality condition. Here I actually have some information to work with, so we can do a little sleuthing here. Yes, here. Good. Oh, sorry. It's okay. We can talk about the condition, right? So the normality condition, we use 30 as a guide. So we have a sample size less than 30, right? We have a sample size of 10. And so we could make a histogram or something like that. But with all this information, right? What I'm going to do is I'm going to look at the largest difference, which I think is 210, right? And then what I'm going to do is if it's super far from the mean, right? So super far meaning the number of standard deviations is more than 3, right? Then I'm concerned, right? Then there might be an outlier and this thing might be skewed, okay? And so when you have all this information, right, you have a few more options. Okay. So since n is less than 30, we need to check for outliers. I'm not terribly concerned about the -50 because if I'm about to check how far 210 is, right, from 80, then -50 is, I think, less than that in distance from 80, -50, yeah, right? And so it's 130 away. Pardon? So this one, oh, yeah, maybe. Sneaky. It's almost like these values are cooked. So we can check both, which I guess we should do. I was just going to check the maximum difference. All right, so we need to check for outliers. We can use the most extreme values, most extreme differences to make sure they are not outliers. Right, and so 210 minus 80 divided by 84.59. Kind of approximately here. $210 minus 80 divided by 84.59. I get roughly 1.537. That's fine. What's kind of our threshold? We're totally happy if it's within 2 and we're okay with 3, right? From that 68, 95, 99.7 rule. Anything within 3 is kind of acceptable, and anything beyond that is a concern. And let's do negative 50 minus 80 divided by 84.59. Negative 50 minus 80 should be the same, just negative 84.59. Negative 1.537. Right, so both of these are within plus minus 2 standard deviations of the mean. So there are no outliers. Keep it on that same page. Okay. If you had the median, then you could just compare the mean and the median. If they're similar, then you know that it's symmetric and the mean is always pulled towards outliers. So if they're similar, then there are no outliers, right? So depends on what information you have. Nice. Now we're ready. From our formula sheet, use it as our guide here. We're going to do a hypothesis test. And I would say the hardest part about paired data is, okay, the mean difference, if I want a one-sided test, then how does it compare to 0? Okay. Takes a little bit of practice, not too much, but step 1, state the hypotheses. So we found that the difference is J minus T. Okay. And if Jocko's estimates are higher than the trusted garage, right? So if J is larger or is greater than T, that's what we're kind of, our alternative hypothesis is. Okay. Then I can rearrange this and I can subtract T from both sides, and then I get, then J minus T is greater than 0. How I like to do it is if you're doing a one-sided test, kind of sneaky, I guess, but just as kind of a guide, if you're going to do a one-sided test, the only side I can go towards with a positive number is greater than 0, right? I use a positive value to prove that it's significantly less than 0. It just doesn't work, right? And so then that kind of gives me a hint as to what my alternative hypothesis should be. So then what happens is that H naught is that mu diff is equal to 0. What's awesome is that's always the case. This is always H naught. There's no change from here if you have paired data, right? So that's one mark in the bag. This is always H naught for paired data. But like I said, the tricky part is the alternative. So then what we want to know is if the mean difference is greater than 0. Took a little bit of work to get there, right? But the alternative is that mu diff is greater than 0, making this a one-sided test. What would the wording be for a question if it was supposed to be a two-sided test? Then I just want to know, is there a significant difference in the quotes from Jocko's Garage and the Trusted Garage? Right, I don't care which way, but here I have this strong suspicion that Jocko's estimates are significantly higher, making my mean difference greater than 0. Kind of tricky. And you guys are on top of things, so I know that you're saying, hey, well, if it's greater than 0 or equal to 0, what about less than 0? Yes, you can absolutely change this to be less than or equal to 0, but I do not. I just kind of ignore it. Okay, that. And you can too, and probably should, because it just makes a mess. But if you want it that way, you can, you're allowed to. Step 2 is do the test, t-test. Calculate the test statistic. So t, remember, it's just the same t, it's just that we're just gonna have little diffs everywhere. And because it's always, the null hypothesis is always that mu diff is equal to 0, that's the same as saying mu naught is 0, right? So it's always going to be 0. So I have it here to emphasize that, but you can just drop it, right? But you are seeing how far is this mean difference from 0, right? Is it significantly different from 0? Or less than or greater than 0? Over S diff over root N diff. So we have 80 minus 0 over 84.59. What was it? 59052. May as well. Divided by the root of 10. 10 carbs. Don't know what's going on with these notes here, but that's okay. I have T is roughly 2.9906686609. Hopefully you get something similar. That's quite large, right? What's it saying? It's saying 80 is almost 3 standard errors away from 0, right? Above 0. So that's kind of okay. I suspect I'm going to be rejecting H naught here, right? So there's going to be clues all along. But step 3, find the p-value. We have to confirm it. So to find the p-value, we need the degrees of freedom, which from the formula sheet is NF minus 1, same as before. Painfully going to go across the page. I have 9 degrees of freedom. Go to the table. I have 9 degrees of freedom. I'll go there first. And also need this lower part. Eek. But I chopped some of that out so I can have this set. So again, you have 9 degrees of freedom. Great. And I want you to use this setup so, because you want to support your answer, right? So since the absolute value of t equal to 2.9907, let's call it there, is between two values on the table, and I'm going to write those down. 2.99 is somewhere in between 2.821 and 3.250. Then below it in the center, the one-sided p, or the one-sided p-value, is between these two values, right? Reading them from right to left, or just write them from smallest to largest, or flip your inequalities. But inequalities are, I don't know. I don't like them. I don't like to think about inequalities, right? And so I just want to have this template and go for it. So now, with a minute to spare, we can write our conclusion, right? If it's somewhere, if the p-value is somewhere between 0.005 and 0.01, that's less than 0.05, which means I have enough evidence to reject H naught and conclude that Jocko's estimates are significantly higher than the trusted garage. I will all write down, but wanted to release you. I'll write it down before I post the notes. Great. We'll do a confidence interval to figure out how much higher, and then take it from there. All right. See you guys tomorrow. Question?
Yeah, on the formula sheet, it says HA is U diff is not equal to 0, but in this it's less than. So
Yeah, so your default is always not equal to, so that's why I have not equal to on there.
you have to